Okay.
Um,
Awesome stuff.
I
Yes,
also
yes.
have a question.
Yes, go
For the
ahead.
table, does it matter? Like, does it affect the equilibrium constant we calculate if we use the ratios differently? Like, if we start using ratios at equilibrium, if we have like one of the
Uh-huh.
moles,
That's
right?
a very
And
good
then
question.
work
That
backwards. Does that change
that
anything?
that is a very good question. In fact, that is a crime that is punishable by absolute failure. Okay? Please, under no circumstances, the only time that you would use the ratio is on this part where we talk about the change. Okay? I cannot emphasize that enough, right? Once you use it here, remember, at equilibrium, you are only talking about the result of what took place. Remember, where's the reaction taking place? It's here. Are you with me, ne? Right?
Yes.
At equilibrium, what you have is a result of what took place in this reaction here. All right. So
Uh,
please, 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 I beg you, ladies and gents, right? The only place where we use the ratio would be only at the change in moles and not anywhere else.
okay.
Okay. Awesome stuff. All right. Awesome stuff. Now, in this case, then what we would do, obviously, for this, because we wanted to find out the Kc, remember we're given the volume. So now we're going to say, all right, number of moles 1.7 divided by the volume, which is 2. So 1.7 divided by 2 would be 0.7. Is it, no, sorry, 85, ne? Is it 0.85? Okay. And then 1.6 divided by 2, that would be 0.8, and 2.8 divided by 2, that would be 1.4. And then ultimately, what are you going to do? Kc, molar concentration of your products. So in this case, you'd have NO. Bona, look at me saying NO. So now we've got SO3, that's our product. Remember the coefficient was 2, so that becomes the power. That's SO2 squared multiplied by oxygen. And all that's needed, Manja, for us is to take the values at the end. So that's going to be 1.4 squared divided by 0.85 squared times 0.8, and that is where we're going to now calculate. Okay, so that's 1.4 squared divided by 0.85 squared times 0.8. Okay, and we get a value of 3.39. Now notice EKC value is greater than 1, so it does mean that we are getting a good yield of the products. It means that we've got more products than there are reactants in that case. And of course, you can see it from the numbers. Okay, right. Are we good, ladies and gents?
Yes,
Yes,
sir.
sir.
Yes, sir.
All right.
Sir,
All right. Yebo.
please ask me. It's kind of
Yebo.
irrelevant to the topic, but then I
Yeah.
want to like clarify, ne, ukuthi,
Yes.
for example, they want the mass, ne, and we're given an
Yes.
equation. So if we're given is it a disulfate? What is it? 2SO2, ne?
Yeah, yeah, yeah. Sulfur dioxide.
Yeah. How do I calculate the molar mass? Does the I don't know how to explain it, but then like that's small 2 at O, ne? Do I also include it? Am I going to say 16 times 2?
If you are going to calculate the molar mass, that's what you're asking, ne?
Yes.
Remember, the only numbers that you consider, you do not consider the coefficient, this number here, right? You only look at the numbers that
Oh,
are at the bottom. So in that case,
okay.
it would be sulfur. So sulfur, I think it's 32 molar mass corner plus 3 times oxygen, which is 16. You see that?
Oh, okay. Yes, sir.
Okay.
Okay.
Yeah.
Thank.
So remember, when you're calculating the molar mass, and by the way, that's a very, very important question. Because remember, when we're looking at the molar mass, okay, the most important thing to always consider is, always check that you don't include that coefficient there. The only exception, man, the only exception is when you've got what we call waters of crystallization. I don't know if you guys know about that. Okay. So sometimes you can have calcium carbonate and then beseba faga something like this. Okay. So we call these waters of crystallization. So it means this would be calcium carbonate that's in crystal form, right? So when you're calculating the molar mass here, you're going to say, well, calcium, I don't know what's the molar mass here, calcium, but uzoti calcium plus carbon, so it's calcium plus carbon plus 3 times oxygen plus, in this case then, uzo include a 10 lo, right? Plus 10 times H2O, so uzoti H2, that's 2 times hydrogen plus another oxygen. Okay, so it's only this one that you add. But if you've got, for instance, in a reaction, 2 calcium carbonate plus hydrochloric acid, when you're calculating the molar mass of calcium carbonate, you do not consider that 2 there. All right. I hope I'm answering your question.
Okay, sir. Mara, what if ne you have
Yeah.
zinc? Is it zinc hydroxide? And it's in a bracket, so I'm not sure if
Oh,
like.
yes. So zinc hydroxide, marangit lelo bracket, that number is at the bottom. Ne? So when you calculate
Yes,
the
sir.
molar mass yakona, then you're going to say, well, it's the molar mass of zinc plus, now that 2 would come here. 2 times the
Oh,
oxygen plus
I
hydrogen.
thought that you multiply. Oh, okay.
Yeah. So,
Thanks.
or alternatively, you can look at it as zinc plus 2 times oxygen plus 2 times hydrogen. Okay.
Okay.
Right. Awesome stuff. Very important question on stoichiometry as well. All right. Moving swiftly along. I think we've got just 2 more questions, and then, Ish, I don't know if we can squeeze in another one. Right. Now, they say to us, when the colorless nitrogen dioxide gas leaves the engine in the exhaust, it reacts reversibly with the oxygen in the air to form a brown gas, nitrogen dioxide, which is a major contributor to air pollution and smog, right? They say write down chemical equation for this reaction. Okay, so Bati, in nitrogen monoxide, nitrogen monoxide plus oxygen forms nitrogen dioxide. Okay, so question, is this a balanced reaction? Absolutely not. So what I would do, put a 2 there. So now we've got 4 nitrogens and put another 2 there. Okay. That is what the reaction looks like. And then they say use Le Chatelier's principle to explain the effect of decreasing the pressure of an equilibrium system of nitrogen monoxide, oxygen, and nitrogen. State also the observation. Yeah. Use Le Chatelier's principle to explain the effect of decreasing the pressure of the equilibrium system of nitrogen monoxide, oxygen. Oh, you remember when I was explaining earlier on, ne? The moment we look at pressure, what do we look at? We're going to check how many moles of gas do I have on the left hand side, right? So you've got 2 plus 1, so you've got 3 moles, right? And then on the right, you've got 2 moles. Now they want to know, in this case, when we decrease pressure, remember we said when we increase pressure, we're going to favor the side with the less moles, ne? But when we decrease pressure, of course, it's going to be the opposite. So once you decrease pressure, we are going to favor the side with a greater number of moles, right? So a decrease in pressure says, look, we've got more space, so we can accommodate more moles. So it means in this particular case, the reverse reaction is favored. Okay, so if the reverse reaction is favored, so what does that mean? It means that we are going to have less nitrogen monoxide, dioxide, and we're going to form more nitrogen monoxide. Okay, and then they also said we should. They said decreasing pressure will have. Okay, so we'll favor the reverse reaction, right? So a decrease in pressure will favor the side that's got the most number of moles. So the products, or it's rather the reactants are favored. So it means that there'll be more nitrogen monoxide and less nitrogen dioxide. And obviously they said state also the observation. It means that the color will turn less brown. Remember, they said this guy is brown in color. Okay. Brown gas, nitrogen dioxide. So it means that we will have a less brown gas forming. Okay. Are we good, ladies and gents?
Yes, sir.
All right. Awesome
Yes.
stuff. Okay. Let's see, with the little time that we've got left, let's see if we can try to squeeze in. I really wanted us to look at this question with, right, even if we don't finish it, but as long as we've been able to dissect, this part of the graph. So sometimes they give us information in the form of a graph. Hey, you guys must admit, nah, it does feel like this camp is short. Nah? Hey, I feel like there's just so many things to touch on. But nonetheless, I think it's there to supplement for, what we do on the channel as well. Okay, so we've got the reaction that is represented by the following chemical equation, which is important for the contact process. Okay, which is the industrial production of sulfuric acid. Right, Batudi adds some more sulfur dioxide and oxygen to the container, and then seals the container. He monitors. Hey, Udikeledi is a guy. Okay, anyway, so he monitors the rates of the forward and the reverse reactions over time. Okay, now note, there are 2 types of graphs that you will have. Some of the graphs will be the graph of concentration, and please, I want you to go and look at the the video that I did on YouTube, right? On that. So some of the graphs that you'll have, you see what you've got three things in that picture, ne? Sulfur dioxide, oxygen, and sulfur trioxide. So if it's a graph, Yama concentrations, you'll see that you would have had three graphs on the same set of axes, right? And you'll see that for the reactants, they decrease, and then for the products, they increase, and then until they reach equilibrium, and then, until a disturbance occurs or whatever the case is. But you have three graphs in that case, right? But now you've got another scenario where you've got a graph for concentration, right? Now, when you've got a graph here, concentration, in that case, no man, not your concentration, your rate of reaction. The two graphs represent the reverse reaction and the forward reaction. Now, if I may just find out from you, which one do you think represents the forward reaction? The solid or the dotted? And why? Not just take a guess.
I think the dotted represents the product. Then no, the dotted represents the reactants. Then the solid represents the product. I think.
Okay. Why?
Because I need to reactants are being used up, so it decreases. Then yeah, you understand. So
I understand. And that's exactly where I wanted you to go to. Remember, these graphs do not represent amounts. What do they represent?
the reaction rate.
Aha. So now you start with reactants. And of course, you are not going to have the reverse reaction taking place. Why? Because you still don't have anything formed on the reactants, on the product side, right? So the graph that you start with is a graph that is going to represent the rate of the forward reaction. So the rate of the forward reaction is this one, the dotted line. You see that the rate is high, and as you use up the reactants, that reaction rate decreases. But what happens? The more I form products, then the products say, oh, Nati, we can now start reacting to form reactants again. So you started with nothing, right? The forward reaction was not there. But as you form SO3, then what you have is you've got the rate of the reverse reaction keeps increasing. And what you'll note with the graph of rate of reaction is that the two graphs always will come to a point where they meet. Okay, why? Because what is the definition of chemical equilibrium, right? This is where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, are you guys with me?
Yes, sir.
Yes,
All
sir.
right. Okay. Now, let's answer the questions. They say, at what time was dynamic equilibrium reached for the first time? Okay. When was it? It was 5 minutes. Can you see that? This is when we reached the dynamic equilibrium for the first time. Okay. And then they say to you, write down the equation for the reaction represented by the solid line. Okay. Now they are very smart. Ne? Sitegonje, the solid line, which reaction does it represent? Forward or reverse?
Reverse.
Reverse reaction. So reverse reaction engine. It's going to be 2SO3, okay, with which will give us 2SO2 plus O2. So they wanted to see whether you understand that this is the reverse reaction. And remember, the reverse reaction has SO3 as a reactant and SO2 and O2 as your products. Okay, right. The next question, what is stately Chatelier's principle? So this is the answer for that guy. Stately Chatelier's principle, remember, we say in a closed system, if one of the factors that affect equilibrium changes, okay, then equilibrium will counteract the change, okay, then a new equilibrium will be established. Okay, there are different ways of stating Le Chatelier's principle. Please just choose one which resonates with you better. Okay, yeah, nothing wrong with the other ways. Okay, right, let's go to the next question because we are fast running out of time. But at 8 minutes, more oxygen was added, ne? Okay, to the container whilst maintaining a constant temperature, right, and volume of the container. With reference to Le Chatelier's principle, explain how the amount of sulfur dioxide was affected when the equilibrium was re-established. Now, I want us to go back to that. Now, they said to us they added more oxygen, ne? Right, now notice, remember that these reactions do not represent amounts, but what do they represent? They represent rate of reaction. Now, the moment I add more oxygen, okay, equilibrium says, hey, sulfur dioxide. The moment I add more oxygen, right, then equilibrium says, hey, we've got more oxygen, we need to get rid of it. Okay, remember that that's Le Chatelier's principle. It says if I add something, I need to try and get rid of it. If I take away something, I need to replace it, right? So the moment I add oxygen, then what happens? The reaction says, hey, I've got more oxygen, I need to use it up. So what happens? The rate of the forward reaction will now increase. Okay, why does it increase? So that it uses up the oxygen that has been formed there. Okay, right. And so as a result, you see that forward reaction, what happens? It surges up, right? For a moment, and then start slowing down. Then remember, the more you now start forming sulfur trioxide, then the reverse reaction starts picking up as well. Okay, and there's that little picking up there, whilst this one is beginning to slow down as well. But at the end, you've got that. Now, in this case, they're asking you the question. Okay, what will happen according to Le Chatelier's principle? What will happen? State fully what will happen to the amounts of sulfur dioxide? Yeah, when the equilibrium is re-established. Okay, so let's go back to sulfur dioxide. Okay, so the moment that we've got a forward reaction that is favored, okay, so we now will form more sulfur trioxide, and what will happen to sulfur trioxide? It will decrease, right? So your oxygen will actually decrease. Why? Because the forward reaction was favored. All right. But of course, over time, in this case, we will then reform that again. But for now, please remember, an increase in oxygen will favor the forward reaction, right? So as to decrease the amount of oxygen, and so it means sulfur dioxide will be decreased. Okay. Right. Next one. They say at 15 minutes, we've got the temperature of the reaction. The reaction mixture was suddenly decreased. Okay, so the temperature was suddenly decreased. So look at this, Right, I'm going to say something here just now. They say from the graph, determine or write down the reaction, which reaction, forward or reverse, was initially favored. So which one was affected the most? Okay, which one was affected the most? Can you see it's that solid line there, right? It had a very, very sharp decrease, right? And I want you to note, in this case, when we decrease temperature, it's the one that depends on temperature the most that will be affected, right? So if you look at this, it means that the reverse reaction, the solid line, is actually the endothermic reaction. Okay? So it means it's the endothermic reaction. So they say from the graph, determine or write down which reaction, forward or reverse, was initially favored. Okay? I'm not sure about that word favored. Okay? But in this case, I know which reaction reacted the most. It would be the reverse reaction. Okay, right. Now they ask the question, is the forward or reverse reaction exothermic or endothermic? No explanation is necessary. Okay, so in this case, remember which one was affected the most? It's definitely that reverse reaction there. So it means that your reverse reaction is endothermic, right? So what does that mean? If the reverse reaction is endothermic, what does that mean for the forward reaction? It means the forward reaction is exothermic. So remember that the forward reaction is exothermic for this reaction. Okay, let's quickly run. They say the following equations may be used to represent the rates of the reaction and the reverse. Okay, where K1 and K2 are constants. Okay, so they're trying to use the equilibrium constant here. They say if the pressure of the system is decreased, okay, by increasing the volume of the container, both the forward and the reverse reaction rates will decrease, but the forward rate will decrease more than the reverse. Okay, right. So once again, once bakhuluma nge-pressure or volume, please go always look at the amount of moles. So we've got 3 moles of gas, on the left hand side. We've got 2 moles of gas on the right hand side, right? So what will happen? In this case, they said if the pressure of the system is decreased, so once it decreases, which one are we going to favor more? So once we decrease pressure, we're going to favor the side with the more moles of gas, right? So decrease in pressure will favor the reverse reaction, and that is what explains what happened there, right? Right, I'm just rushing through this because of time. Okay, they say at 15 minutes, the temperature of the reaction mixture was suddenly decreased. Okay, from the graph, I'm repeating that thing again. Okay, consider the rate equation provided and state why a decrease in pressure causes both the reactions to decrease. Now, please remember, for this one, why would it affect both? Remember that concentration is number of moles over volume, né? Right? So once you decrease the volume, once you increase the volume, okay, what happens to the concentration? The concentration decreases, right? Even if the number of moles stays the same, but by definition, an increase in the volume will decrease the concentration. Okay, right. And then, but with reference to the equations provided, explain why a decrease in pressure causes the forward reaction rate to decrease, more than the reverse. Okay, and we did explain there, okay, as I did say, that because we've got more moles of gas on the right hand side, in this case, we actually will favor the reverse reaction in that particular case. All right.